Okay, for 1.1 number 1, we're asked if f of x equals x plus the square root of 2 minus x and g of u equals u plus the square root of 2 minus u, is it true that f equals g? And this one is going to be true or yes, because it's literally the same thing. Yeah, when you see a question like this, it's generally going to be related to a whole or lack of a whole. Just like it is in number 2, where we're asked if f of x equals x squared minus x all over x minus 1, g of x equals x, is it true that f equals g? So we're going to say no or false. The simplification for this would generally go, you would factor out an x, and then you would get x minus 1 in the numerator, and x minus 1 in the denominator, and then these two terms would cancel out, and you're left with just x. But kind of like a problem that we did last week, right, this isn't just x, this is x with a whole at x equals 1. So that would be false, because f has a whole at x equals 1. So, okay, now 3a. Given the graph of g, state the values of g of negative 2, g of 0, g of 2, and g of 3. So at least for a, we'll denote these answers in yellow. So g of negative 2, so we're just being asked to pull from the graph. Okay, this is kind of a bad example, but well, not bad, but it's just hard to pull from the graph. Let's say this is about 2, right? Because we could say that this point is about here. If you're actually given this like on a quiz or something, it would definitely be drawn much better than this. But you know, I'm no artist, obviously. G of 0, however, which we'll denote with a green, right? We can look at the graph and see that it is negative 3, right? Because all the way down here. So that's going to be negative 3. G of 2. Running out of colors here, but we'll use brown. G of 2, so we're going to be looking at this x-coordinate, this x-coordinate right here. And we have two options. We've got an open hole and a closed hole. Whenever we're talking about the value of something at a point, we always use the closed hole. So we will say that G of 2 is 1. And it is not 3, because we always go for the closed hole. Okay, so G of 3, 1, 2, 3, again, not super well drawn, but we'll say it's 2. Okay, now for 3b, we're asked for what x values is g of x equal to 3. So that's asking us where on our graph is our y value 3. So we could like draw a horizontal line or something like that. And the only point where we equal 3 is at x equals negative 1, 2, 3, 4. And so that would be x equals negative 4. Okay, now for 3c, for what values of x is g of x less than or equal to 3? And that is going to be everything in our domain. So you can see here we are defined from negative 4 all the way to positive 4. So that would be our answer here. Notice that we do not say negative infinity to positive infinity, and that's because our function, as far as we know, is only defined from negative 4 to positive 4. If we had arrows on the end like that, or something along those lines, then we could say negative infinity to infinity, because those arrows imply that the function goes on forever. But since we don't have those arrows, we cannot assume that, and we have to assume it's just what we see here. And what we see here is from negative 4 to positive 4. Okay, so now we need to state the domain of G, domain and range of G. So that's just, well, we already said the domain, right? Negative 4 to 4. And then the range is going to be all our possible y values. So our lowest y value is -3, right? And that's inclusive, right? Because we can be -3. And then our highest is going to be +3, which we get right here, right? So our domain is going to be -4 to 4, and our range is going to be -3 to 3. Okay, so now we're given these two graphs here, and we're going to answer some questions about them. So the first one is f of -3 or g of -3 larger? And so we can see that these two functions intersect at +2 and -2. So, and the red function, which is g, is going to be increasing after that point, whereas the green function is going to be decreasing. So we can kind of look at the two respective points here, or sorry, I guess we're talking about -3. So we kind of look at it here, here and here, and we can see that obviously the red point is higher, so g of -3 is going to be larger because it's got a larger larger y value. Okay, so now for what x values is f of x equal to g of x? Well, we can see that it intersects here at -2 and +2. So we would say x equals -2 and +2. Now, on what interval is g of x greater than f of x? So g of x is greater than f of x on, where's brown? Here we go. This interval and this interval, right? And since it has the endpoints, this means it's going to be from -infinity to -2, and then again from 2 to infinity. And, parentheses. And keep in mind that we use open parentheses on our two endpoints here for -2 and 2 because, this is in the wrong spot. Actually, so sorry, I misread the question. This would be closed brackets here because we are dealing with less than or equal to. So since it's equal to, we use the closed brackets because it is equal to, f of x is equal to g of x at that. If we did not have the bar underneath to imply that it's less than or equal to, then we would have the open brackets. But since we do have that, since it is less than or equal to, then we have the brackets instead of the parentheses. Okay, so now state the domain and range of f and g. So so both of these are polynomials. So it's -infinity to +infinity for both of those, and if you're ever asked to state a reason, you could just say it's a polynomial, or like it's a parabola, or it's parabolic. It's just say it's a polynomial, and you're going to be fine. The range is a little bit different for f. Let's start with g. So for g, the range is going to be, what do we bottom out here? What do you say, like +1/2? So something like +1/2 all the way to infinity. And then for f, we top out at 2. So we say we're from -infinity to 2. And then we use the curly brace on the endpoint because that is our vertex of our parabola. So if you're ever dealing with a parabola, your vertex will always have a closed endpoint. Unless, of course, you have a hole, but that will usually be pretty obvious. So, okay, now determine if y is a function of x in the following functions. So this is basically just, does the function pass the vertical line test or not? So one way you can do that is you can solve for y. So in this scenario, right, you could add 5y to both sides. So then now you got 5y equals 3x minus 7, and then divide them all by 5, so y equals 3x minus 7 over 5. That is a completely normal function. It's a polynomial, so that's totally fine. So we would give this one a check mark. So that is a function of x. Moving on to number 8, this is what we're looking at. So we could do the same thing. We could say, okay, y equals 3x squared minus 5 all over 2. And that is also a polynomial. So that is going to be defined everywhere. So we're going to be okay there. Now for this one, number 9, we have a bit of a situation here. So we've got, let's move that x over to one side. So y minus 3 squared equals 5 minus x squared. So then we would go and we would take the square root of both sides, and we would get y minus 3 equals plus or minus the square root of 5 minus x squared. Now, then, right, we could say, well, okay, y equals plus or minus the square root of 5 minus x squared plus 3. So, but you don't even have to go that far, because any time you get this plus or minus, that's a problem. And whenever you get that plus or minus, you end up with a circular graph. So I believe the graph of our function would look something like this. Like we'd have like a circle kind of here floating above the x-axis. So anytime you end up with a plus or minus, it's usually a sign that it is not a function of y. So we would say that this is not a function of y. So we would give that one an x. And you can generally tell whether or not a function is going to be a function of y. If your y term is squared, then it's probably not going to be a function of y. And we're going to see a similar thing here. So we could factor out a y from both terms. Equals 4. Oops, sorry. Equals 4. And then we could divide both sides by y. But then we've got two different terms here. So this is just, if you've got multiple y's going on, if you've got a squared y term, it's not going to be a function. Y is not going to be a function of it. However, when you have your y term to an odd power, like we do here, and like we do here, just the odd power is 1, right? But if you have it to any odd power, that can be 3, that can be 5, that can be 7, that can be 381. If your y term is to an odd power, then you're going to be just fine. And we could do the math on this, and it would be like y equals the cube root of 2x minus 1, and then all of that minus 3. And the key difference here is when you take the radical of an odd power, you don't pick up that plus or minus that you did when you took the radical of an even power. So this one would be a normal graph. So this one would get a check mark. And this one's a little tricky. Probably very obscure knowledge. This one would not be a function. The absolute value function it's kind of just a weird edge case, just kind of messes everything up. It falls into the same category of the even powers, where you get a function that fails the vertical line test. If you want, you could graph it on Desmos graphing calculator or something if you just want to see it. But generally speaking, if you're taking the absolute value of your y term, you're probably not going to pass the vertical line test, and so y will therefore not be a function of x for that problem. So that one gets an x. And then we've also got tables. So the rule of thumb is you can't have repeat x values in your table. So, for example, here we've got 60 twice, and it's got a different y value, right? It's got 8 here, and it's got 7 here. So if you wanted to picture that, right, so we got 60 over here, we've got 8 here, and we've got 7 here. We've got a point up here, and we've got a point down here. There is no way this can be like a normal like line, you know what I mean? Like there's no way without going straight up and down, which is a vertical line, so duh, we fail the vertical line test. There's no way we're a continuous function on there. So if you have repeat x values with different y values, you fail the vertical line test, and that's what happens there. If, however, you have repeat y values, so something like this, so let's say, what do we got here, 2018 and 2019, and then we hit 11,200 twice here. So we've got these 2 points on here, so we can do this between the points if we want. We could just go straight line, we could do something like this. All we fail here is the horizontal line test, but the horizontal line test is a completely different thing, right? We can have a horizontal line, that's not a big deal, that's totally fine. So we can have repeat y values, we just can't have repeat x values. So that's why number 14, it's supposed to be numbered 14, sorry about that. That's why number 14 would pass, would be a function of x, but 13 would not be. Okay, now moving on to section 1.2. So the first thing we want to do is we want to state the domain of cosine of x divided by 1 minus sine of x. This is a really good problem for practice just because it combines your unit circle and it combines your knowledge of like domains and ranges and stuff. So let's just start by setting the denominator equal to 0, because if there's one thing that makes a function undefined, it's definitely a denominator of 0. So 1 minus sine x, we set it equal to 0, so 1 equals sine x. We take the inverse sine of both sides, sine inverse of 1 equals x. That's asking us, okay, on your unit circle, what pi values give you a sine of 1? So remember, cosine, sine, that's your ordered pair. So 1 is all the way up here, and then so that's going to be right pi over 2. So our answer would be pi over 2, but then also, right, because if you recall the graph of your like cosine, for example, right, it looks something like this. Like it keeps going up and down and up and down and up and down. It repeats every 2 pi, right? Because 2 pi is one full rotation around a circle. So we say plus 2 pi, and then there's some constant. I'm blanking on the constant. I think it's like s. 2 pi s. Here, let me look it up real quick. Okay, it's n. It's just 2 pi n. So you say 2 pi n for it repeats every 2 pi. So we would say that the domain is just where x does not equal pi over 2 plus 2 pi n. So it can't be pi over 2, and it can't be that plus 2 pi times any number. Okay, so now graph the cubic function if f of 1 equals 6 and f of negative 1 equals f of 0 equals f of 2 equals 0. So this is an interesting question. You might notice that sometimes I don't copy the questions from the textbook verbatim, and that's generally just because I feel like sometimes there's a more interesting way to express these to just kind of work more like math concepts, I guess. And I think graphing is more interesting here. So all this whole thing really says is that f of negative 1 equals 0, f of 0 equals 0, and f of 2 equals 0. So it's just saying you have 3 different zeros, one at x equals 1, or sorry, 1 at x equals -1, 1 at x equals 0, and 1 at x equals 2. And then tells you f of 1 equals 6. Okay, so then that would be, this goes up here. So we're told that it's cubic. So the cubic function means it's to the power of 3, right? So we're dealing with something like that. The number of turns a graph has is the degree minus 1. So what does that mean? So if we have our function here, right, and it has to do something like this, our function's degree is 3 because that's the power that it's to. So if its degree is 3, it has 2 maximum turns. So it turns here, it turns here. So that means it can't turn anymore. So that means here it must keep going up to negative infinity, and here it must keep going down to positive infinity. Okay, number 19. I definitely truncated this question quite a bit. So it costs $2,200 to make 100 chairs in one day, and $4,800 to make 300 chairs in one day. Express the cost as a function of the number of chairs produced, assuming it's linear. Sketch the graph. So we have, this is like your rise over your run, your f of b minus your f of a over b minus a. This is a function that, or not a function, a calculation, I guess. Formula, sorry, there it is, formula. This is a formula that you'll be using a lot throughout the semester. So if we say our b, so if we say the number of chairs is our x, number of chairs is our x, and then the cost is our y. So then our f of b, or our y, would be 4,800, because our b would be 300 chairs, right? So we're just kind of linking these two numbers together. One of them's our x, one of them's our y. And then we're doing the same thing for the 2,200, that's our f of a. And then that would make the 100 our a. So now we're dealing with something like this. So we can simplify that, right? So that's 2,600 all divided by 200. Cancel those zeros out, and then so that would be 13, right? Because 26 divided by 2 is 13. So that would be our slope. And here, so I guess we'll answer B while we're at it. Slope is 13, and that is the number of chairs, or number of dollars per chair. And then what is the y-intercept? Oh, we gotta find that still. So you might remember point slope form. Point slope form is, okay, I'm gonna do these calculations down here. Point slope form is y minus y1 equals m x minus x1. So then we plug in a point on our graph, and we'll just do the one with the smaller numbers, right? Because that's just generally easier to work with. So y minus 2,200 equals m being our slope. So 13 times x minus, and then if our y value is 2,200, right, our corresponding x value is 100. So we're dealing with something like this. So y minus 2,200 equals 13x minus 1,300. We add 2,200 to both sides. So y equals 13x, and then that is plus 900. Yeah, so plus 900. So our intercept is 900. So this would be the base cost for a day, I guess you could say, or base operating cost or something like that. So that's how you would use, your rise over your run, your f of b minus f of a over b minus a, and your point slope form to generate an equation. Definitely a very useful skill. We use a lot of point slope form in Calc 1, so this is a formula you will definitely need. But I mean, it's probably a formula you've been using for years now, so not a bad formula to have to know. Okay, so now section 1.3. The graph of f is given. Write equations for the following transformations of f. So this is just saying we have some function, and a is saying let's shift that function up. So we do f plus 3. Shift f down 3. Okay, f minus 3. Shift f right 3. Oh wait, here, let's do of x. Sorry. Oh my gosh. Okay, so f of x plus 3, f of x minus 3, f of x minus 3, because this is kind of like the problem we did last week with the completing the square and then doing it as like transformations and stuff like that. When you subtract inside of the parentheses, you're moving right. And when you add inside the parentheses, you're moving left. If we want to reflect about the x-axis, we just take a negative sign out front. If we want to reflect about the y-axis, we take a negative sign inside of the parentheses, right? Because you kind of could think about it like, okay, if we have x squared and now we want to flip it upside down or just reflect it about the x-axis, right? That's just the graph of negative x squared, right? That's kind of what I think of. I always think of, okay, what do we got to do to x squared to get it like that? And then reflecting f about the y-axis, well, that's x squared is a bad example for that because it's symmetrical, but you get the idea. Stretch f vertically by 3. So we would take a factor of 3 out front. Shrink f vertically by 3. Then we would take a factor of 1/3 out front. So if you want to stretch by a factor, you just take that number out front. If you want to shrink by a factor, you take 1 divided by that number as a factor out front with like the 1/3. Stretch f horizontally by 3. So this is, we do it inside of the parentheses. Shrink f horizontally by 3. So this would be f of 1/3 times x. So horizontally is just doing the stuff inside of the parentheses. Okay, so now graph of f is given. Use it to graph the following functions. We got f of 2x, so this is kind of like doing a vertical, or I guess this is technically a horizontal stretch by a factor of 3. So in this case, we would start at the same point because x times 2 is 0, or sorry, 0 times 2 is 0, so we would start at the same point. Now for the corresponding point for x equals 1, we would go 1 out. For the corresponding point for x equals 2, 2 times 2 is 4, so this point would be out here. For 3 times 2 is 6, so this point would be here. Times 4 is 8, so we would be like down here, and then like somewhere out here for 10. So we would look something like that. And okay, this is probably gonna get kind of messy kind of fast. But then for the 1/2 thing, similar story, just instead of stretching it, we like shrink it. Crap. So this would go there. This 2 would go here. We would also start at the same point. This is 3, so that would go here. 4 would become 2. And what is this? 6. 1, 2, 3, 4, 5, 6. 6 would become 3. So we would be left with something like that. Now for f of negative x. Oh my gosh, why'd I make that red? Let's make it brown instead. So f of negative x, so this reflects it across the y-axis, taking that negative, right, because that's what we said here. So we start at the same spot like we always do. The corresponding point for f of 1 is just going to be the same, except for it's just at f of negative 1. For 2, same deal, right? And then 3, same deal. 4, same deal. 6, same deal. So it's just reflected across the y-axis. Not too bad. Now we've got negative f of negative x, which is a reflection a reflection across the x and the y-axis. So what that looks like is we don't start up here for once, if you can believe it. We're going to start actually down here because our beginning y value is 2, right? So, but since we've got that negative out front, our starting value for this one is negative 2. So we're going to start there, and then we're just kind of going to fill it out like a flipped version of that. And we will actually cross over here. So it'll look something like that. Again, not necessarily drawn to scale. I'm a pretty terrible artist, but you get the idea. So that's how that goes. Okay, so now section 1.4. So we're going to use the laws of exponents to rewrite and simplify the plethora of expressions we have here. So to start with A, we can rewrite 2. Let's rewrite 2. So 2, and we can kind of use one of the squared. So right, 2 squared is 4. And if we square something, we've used up 2. We've used a factor of 2 out of the exponent. So we're left with 4 cubed divided by 4 cubed, which is just negative 1. Okay, so now for B, we could say that we could take this 6 and we could use up 2 out of this 6 to make this 9, because negative 3 squared is 9. So, but then we have to factor out a 2 from this exponent. So that would be 9 over 3, and then divided by 9 over 6. But then this is just simple exponent math. We can simplify this as 9 to the 3 minus 6, which is 9 to the negative 3, which is 1 divided by 9 to the third power. And you could simplify that even further. That is 81 times 1 over 81 times 9, but I don't know what that is off the top of my head, and I don't think you'd be expected to either. So C is relatively simple. We can rewrite this as x to the negative 5/4 power. This is definitely a rewriting that you will have to get very comfortable with, especially if you have to take like Calc 2 or whatever. But the back half of this course and like all of Calc 2, you'll be rewriting a lot of radicals like this. Essentially, when you take the whateverth root of a thing, that radical goes into the denominator. So this gets rewritten as 1 over x to the 5/4. And then since it's in the denominator, you take a negative exponent and bring it up to the numerator. Or you could leave it in the denominator. It depends what you want to do with it. It depends what the question is asking you to do with it. So this could be rewritten as x to the 5/4 or x to the negative 5/4. This is a slightly more simplified term, although it's generally unacceptable to leave a final answer with a negative exponent in it. But that's a bridge we'll cross when we come to it. Just either one of these works for now. Okay, x to the 3 times x to the n divided by x to the n plus 1. So we can rewrite this as this x to the n plus 1 as x to the n times x, because addition within the exponent is the same thing as multiplication outside of the exponent. So then this x cancels, well, it doesn't cancel, but it makes this a 2, and then it straight up cancels with this. So this is just x squared. So then, next up we've got this, and exponent within the exponent is the same thing as multiplication. So this essentially becomes 3 to the negative 2 times b to the positive 2 all times b cubed. So then that becomes addition between this term and this term. So that is 3 to the negative 2 b2 plus 3, which is 5. So you get 3 to the negative 2 b to the 5. That's what you get there. That's all right. So now here we are, oh, this looks terrible. So we are, I guess we'll simplify this first. This 3 becomes a 9. This x squared gets squared, so that becomes x to the negative 4, because, right, exponents outside of the exponents become multiplication within the exponents. I don't know if I'm even making sense. It's pretty late. And then it would be 2x squared y. So then we would get this y to cancel with that y. That 2 and that 9 can't really cancel, but then this x would combine to be a 2/9 times x to the 6th, because this x minus 4, right, or x to the negative 4, when it comes up into the numerator, it becomes positive, because, right, remember how we said here, when you take a exponent from the denominator and you bring it up to the numerator, you take a negative. So that's essentially what happens here. We take a negative of the negative 4 in terms of the exponent. So we actually get x to the 6th up here, and then we could say y to the negative 1, or we could leave y in the denominator or something like that. And we could also like move this 9 down into the denominator or something. There's a lot of different ways we could write a lot of these. In my opinion, this is the most aesthetic way we could write it, so I guess that's how I'll write it. Okay, God, I really should have left more space here. So, all right, so for g, right, we're dealing with this. So whenever you see this, it's usually a hint that you need to factor out a perfect cube. So a perfect cube, so I'm just going to divide 108 by 4. So that's what, 2, 8, 2, 8, and then that is 6, no, 7, duh. Yeah, all right, so 27. So if we can rewrite this as 27 times 4, right? Because 108 is 27 times 4. That's another way you can write that. And then you can take this 27 outside. You can split this up into this cube root of 27 times the cube root of 4. The cube root of 27 is 3, right? That is a perfect cube root. So now it's 3 times the cube root of 4 in the denominator. This cube root of 4 cancels out with this cube root of 4, so then you're left with 1 divided by 3, so you get a third. I don't even know what this one is asking you to rewrite. Oh, never mind, I get it. Okay, so this is the same thing as the cube root of 27 squared. This is actually a really important one, very basic one too, but the fraction becomes the root, or sorry, the denominator in the fraction becomes the root of the radical, and then the numerator stays as the modifier within the radical. Again, that's a super prominent, super commonly used method of rewriting and substitution and stuff that you're going to use a lot throughout this course. So definitely be familiar with this kind of operation. And like also this kind of operation too, you know what I mean? Okay, so now this stuff, so it's going to be 2x squared times, it's 9, or 3 squared is 9, x to the 5th squared is x to the 10, because exponents outside become multiplication inside. So then this is what, 18x to the 12, because multiplication between two exponents becomes multiplication outside two exponents becomes addition inside. So we get 18x to the 12. Okay, so now here, you can hardly see it, but this is going to be 2x to the negative 2 all to the negative 3 times x to the negative 3. So we've got 2 to the negative 3, and then x, and then we said exponents outside the exponent become multiplication within the exponent. So x to the 6th, because negative 2 times negative 3 is 6, and then it's all times x to the negative 3. So, right, multiplication outside of the exponent becomes addition inside of the exponent. So 6 plus negative 3 is regular 3. So we've got 2 to the negative 3 times x to the 3. So this could be rewritten as x to the 3 divided by 2 to the 3. 2 to the 3 is just 2 times 2 times 2, which is 8. So we could say x to the 3 over 8, or like 1/8 x to the 3, or whatever you want, honestly. Okay, so then 3a to the 3/2 times a to the 1/2. So, right, we said multiplication outside of the exponent becomes addition inside of the exponent. 3a, 3/2 plus 1/2 is 4/2, which is 2, divided by a to the negative 1. So we can bring that up, so it becomes times a to the 1, right? Because we brought it up into the numerator, took a negative exponent. Multiplication outside of the exponent becomes addition inside, so it's 3 times a to the 2 plus 1 power, which is 3a to the 3rd power. Okay, so now we're dealing with this, so square root of a b to the 1/2, right, because we can rewrite that as 1/2. This bottom can be rewritten as the cube root of a times the cube root of b. I don't know why you would rewrite that. I don't know, I'm just kind of trying stuff, I guess. So then this numerator would become a to the 1/2 times b to the 1/4, because 1/2 of 1/4 is, or sorry, 1/2 of 1/2 is 1/4. So then this is a to the 1/3 times b to the 1/3. So then this simplifies to a to the 1/2 minus 1/3 times b to the 1/4 minus 1/3. And that's because these powers get brought up to the numerator, right? And they become, that becomes a to the negative 1/3, right? And then a to the negative 1/3, or sorry, a to the 1/2 times a to the negative 1/3, multiplication outside of the exponent becomes addition inside of it. So this becomes 1/2 plus negative 1/3. And then for b, it would become 1/4 plus negative 1/3. So then this becomes 1/2 minus 1/3 is a 1/6. So that becomes that. And then 1/4 minus 1/3 is a negative 12th, I want to say. Yeah, I believe that is true. So then that would become a to the 1/6 divided by b to the 1/12, and then that would become the 6th root of a divided by the 12th root of b. You would almost certainly never be given anything this difficult on a practice test, but it is a useful thought experiment. You're going to be dealing a lot with exponents over your calculus career, however long that ends up. Okay, then finally, section 1.5. I kind of just wanted to throw in some general knowledge at the beginning because stuff about functions and one-to-oneness and stuff is kind of scattered throughout section 1, and so I just wanted to clear it up. It's really not that hard. Just a function is no repeat x's, aka it passes the vertical line test, which means if you draw a vertical line and you want to move the vertical line, you can, and you don't intersect two different lines. You know what I mean? You guys know the vertical line test. And then one-to-one is no repeat y's, so it passes the horizontal line test. So all these functions are vertical line compliant. An example of one that wouldn't be would be like, I don't know, like a circle or something like that, right? Because then you would draw your vertical line and you would fail, right? Because you're touching 2 points here, you're touching 2 points here, you're touching 2 points everywhere. So it would fail that. But, you might be asked, does it pass, or is the function one-to-one? Does it pass the horizontal line test? So same thing as the vertical line test, you just do it with a horizontal line. This function is doing just fine. This function, however, y equals x squared, right here, look, it's touching in 2 points, touching in 2 points, touching in 2 points, everywhere. So this would fail. This function is fine, right? Because it is never touching the same y value. But this one, unfortunate. So generally speaking, your functions that are even powered will fail. Here, I'll write this down. Even power, not one-to-one. But your odds, one-to-one. Generally speaking, and right, if you're given a complex function, you would definitely need to do something more nuanced to actually figure it out. But generally speaking, right, your parabolas are going to fail the vertical line test, but then your x cubes and your x to the 5s and your x to the 1s, right, you're just regular lines, they're going to pass it just fine. So I just wanted to give a brief overview about that. It's an important thing to know, and it shows up on a lot of different units that are covered in this pre-quiz material, which makes me feel like it will be pretty important and you could definitely be asked a question or two about it. So just know one-to-one. Okay, and then for this one, this is just like, so when you have 1 minus like the x squared and stuff like that all inside the square root, you end up with this weird semicircle thing where this is your entire thing. So if we want to state the domain and the range of this, right, the domain is -1 to 1 inclusive, so you have the closed brackets. The range is 0 to 1 inclusive. And then if we wanted to find the inverse of it, it would literally just be this, and then it would go down here. And you could do the algebra for this, but this is what it would end up looking like. And the domain of this would be 0 to 1 inclusive, and then the range would be from -1 to 1 inclusive. So it would just flip-flop around, which is actually a general feature of inverses and stuff like that. The domain of your base function is the range of your inverse function, and the range of your base function is the domain of your inverse function.